much. Good morning. I'm Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We are arranging a lecture series on X-ray crystallography and solid-state chemistry. This is our 20th lecture on X-ray single crystal diffraction. We have been talking in the slides last slide about reciprocal lattice points. And here you in the right, you will see that this is a reciprocal lattice point generally taken by Weisenberg upper layer photograph. But you see, the intensities here are shown almost identical. In real case, we may not get this identical intensity of this reciprocal lattice point. Okay, from here we can find out. The unit cell of the reciprocal lattice. Come to here. We draw axis here in this way, the S star axis, in this way the B star axis. The C star is perpendicular to the plane of paper. Why you take this as S star and this as B star? You see, if we look to this, and we will say there's a mirror image of other lines of reciprocal lattice points. If we go this way, we will see that this is a mirror image of this line. So therefore, it is a mirror image. That means we have two mirror images perpendicular to each other, and if we take the three-dimensional one, then we see that it's a three mirror image perpendicular to each reciprocal lattice axis. So from here we can draw the unit cell. This is the unit cell of the reciprocal lattice. Now this is what we call 0, 0, 0. This is the origin A, and then we have 1, 0, 0, and then we have this point 1, 1, 0, and this is 0, 1, 0. This is how we index it. So now we have the origin, we indexed it, and then we'll see the real unit cell of the crystal is this indices 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. It is related inversely to the real unit cell of the crystal. Note, however, the reciprocal lattice unit cell serves not only to identify the repeat unit of the reciprocal lattice. And you see that here it does not meet the real space criteria. What is the real space criteria? The real space criteria is that repeated unit cells have identical. But here you can see that it is not exactly identical with the intensity. But anyway, we can see the spot intensity here. 100 and 200 differ in adjacent unit cell of the reciprocal lattice. Another thing, we can see that D spacing, that is D100 and D010, represent the two of the longest possible D spacing in real space. Okay, and then for instance, twice of the values of D200 and D020 in the reciprocal lattice point of 100 and 010 closest to the origin. 100, 100 and 010 are the closest to the origin. And it has got half distance of these 200 and 020 along the A star and B star. Well, we have been saying about that not only that how to find out unit cell and how to find out the symmetries it consists. Okay, so lattice type, there are certain rules which are the reflection to be observed and which we do not observe. So in primitive lattice, we know that no restriction is there. All reflections could be observed because it has got a symmetry, that is one bar symmetry, that is at 360 degree, or if an object is rotated 360 degrees, it's the same. So therefore, here we do not get any rules for reflection to be observed for primitive lattice. But for other lattices, for example, body-centered lattice, face-centered lattice, side-centered lattice, rhombohedral lattice, they have some reflection to be observed condition. For example, body-centered, we see this H plus K plus L is equal to 2n. For face-centered, we will see that HKL either all odd or all even. We do not get odd or even together. For side-centered lattice, see, we have H plus K is equal to 2n. For rhombohedral lattice, HK is equal to minus H plus K plus L. These are the reflections we will be observing in our reciprocal lattice point. Okay, next slide. We are talking about in this figure. We are talking about one thing we should say here. We assume that all reflections have equal intensity. This is not in the case when we try our actual experimental data. Well, the condition for this reflection for body-centered lattice and orthorhombic structure, we are talking about body-centered lattice of orthorhombic structure. So here what we have to find, H plus K plus is equal to 2n. So let us say here 2n. It should be always even then. Okay, 2 plus 0 plus 0. So it's 2. So H plus K plus n is equal to 2n. Hence, in the 0 layer, this is the 0 layer, HK is equal to HK is equal to what you get, H plus K is equal to 2n. You can see in here always we are getting H plus K is equal to 2n. And we will see that 1, 0, 0 or 0, 1, 0 or 1, 2, 0 or 2, 1, 0 are systematically absent. If we go to the next layer, that is HK1, what you see, the condition are opposite, that H plus K is equal to 2 plus 1. So we get 0, 1, 1, 1, 1, 0, 1, 1, 2, 1, 2, 1, 1 are observed, whereas this 2, 0, 1, 0, 2, 1 and 0, 0, 1, 1, 1, 1 and 2, 2, 1 are systematically absent. If we go to the next layer, that is HKL is equal to 2, the same appearance of 0 layer we will see. And if we go to the third layer, it's like exactly the first layer and so on. So in conclusion, what we can say, in order to identify unit cell and lattice type from diffraction pattern, it is usually necessary to have information on upper layers, and only 0 layers will mislead us to find out the lattice type in the structure. So we have to take 0 layers photographs and upper layer photographs to conclude about the lattice type of the crystal we are under experiment or so. It has become apparent now that how the inspection, the superimposing of two diagrams A and B, that the pattern allowed reflections from a face-centered lattice in 3 dimensions. So if we come to this here, that the face-centered reciprocal cell has no real significance as such, but it does allow us to understand the rather obscure but often repeated statement that is a body-centered lattice is a real space, gives rise to a face-centered lattice in the reciprocal space. Body-centered lattice is real space. It gives rise to face-centered lattice in real space. In this figure, what we show, shown a face-centered lattice F for which condition that HK are all even or all odd. Here you see it's all even. This HK0, you can see all reciprocal lattice points are either all are even. Here you can come to here, you will see that all are odd. So this is the condition for face-centered lattice we discussed earlier. So a face-centered lattice is in real space, gives rise to a body-centered lattice in reciprocal space. So this is the information we get from the data we are getting for single crystal data, either by film method or by diffraction method. Okay, next what we're going to see, we are going to talk about a rhomboidal lattice occurs in some hexagonal unit cell. Here is the hexagonal unit cell for rhomboidal lattice. This is the HKO layer of the reciprocal lattice. So here is the hexagonal unit of the rhomboidal lattice. So here we can see that zero layer we have superimposed here three layers: zero layer, first layer, and second layer. And mind that from here we can find out the systematic absence for this rhombohedral lattice, which rules. The rule is this: HKL is equal to minus H plus K plus L must be is equal to 3N. And this is followed here in these figures A, B, and C. In context of C, what we say that sometimes if we take three sections reciprocal lattice, we can also have rhomboidal lattice which is trigonal or hexagonal axis. Not hexagonal axis, it could be trigonal also. Okay, we go to now a little bit more systematic absence or condition for a deflection to be observed. By extinction, we have talked about it. We said it extinction or systematic absence or condition for a deflection to be observed. So we are now talking about, we have been talking about lattice type and not very much of symmetry elements, but point symmetry elements we have discussed in our data. We need to know about the space symmetry elements also. We have to find out the space group before we start taking our data. So as possible space group also, or with the help of systematic absence and lattice type, we can conclude the possible space groups of the crystals and crystal under consideration. And then we proceed to collect the data, and after that we reduced the data, which we call data reduction. So when we are associated with space symmetry elements, and we know that we have light lens and screw axis. Okay, a primitive lattice, reciprocal lattice that contain all possible lattice points in diffraction system. Those do not meet the criteria required by a particular space symmetry elements may be deleted. Okay, for example, that we take an effect of this statement, for example, the effect of two fall screw axis, which is parallel to C, and in that case, what we get 00L are systematically absent for odd values, that is 001, 001, 003, 005 are absent. However, the only even values are present. So 002 and 004, these are the even values which you will observe. Screw axes are always parallel to unit cell axis. Either it would be parallel to C axis, or either it will be parallel to B axis or A axis. Here we have some condition for two-fold screw axis, four-fold screw axis, three-fold screw axis, parallel to C axis. Our condition is 00L is equal to, where L is equal to 2S. Three-fold screw axis, and then six-fold screw axis, and parallel to C axis. This condition here is L is equal to 2N. If it is this type of screw axis, four-fold screw axis, parallel to C, the condition should be 4N. And for six-fold screw axis parallel, the condition should be 6N. 00L, 6N. Glide planes, we do have B glides, C glides, N glides, D glides. And for these glide planes also, if glide planes is perpendicular to A, what we get? KL, where 0 KL, where K is equal to 2F. If it is C glide perpendicular to A, so 0 KL, L is equal to 2N. N glide, if it is perpendicular to A, you get 0 KL, A plus L should be 2N. And D glide perpendicular to A, if it is 0 KL, then A plus L should be 4N. These are the points one has to carefully note in the observed data. Okay, I've taken this chart also. Now we go to next slide, and the diamond glide occurs rather infrequently only in which are the crystal system, where you can get diamond glide, orthorhombic system, tetragonal system, and cubic system. So we need not to look for diamond glide when we find that the crystal systems are, say, monoclinic, triclinic. You need not to look for diamond glide plane. So systematic absences in lattice, centered lattice by the cancelling diffraction from certain lattice planes. Absence due to symmetry elements have a similar origin, and with this symmetry elements and lattice type, we can arranging this and taking into consideration of lattice type and space symmetry elements, we can predict the crystal which space group it belongs to. Now, we have taken data. So there are some problems in taking data, experimental problems, and these problems had to be taken into consideration when we have our real data set to reduce the data, we would call data reduction. So these are those problems we have to take into consideration very carefully before we take data. So you see, here I showed a white radiation streaks in reciprocal space. The radiation we are using always accompanied with white radiations. And when we expose our crystals in the radiation, then not only that we get reciprocal lattice point, but we also get some additional intensity. And this looks like this, that streak lines. This is the streak line. This is three axes, and we can see that these streak lines are going. But there has to be eliminated. That means background intensity has to be eliminated, for which there should not be any streak in the observed, the integrated intensity data. I show this figure here showing that how this is a limiting sphere of reflections. This is a limiting sphere, and this is the data we are getting in the film. This is where is our film. Get this data. This X-ray source and beam stoppage here. So we get this data. You see, this is a streak here. So these are the streaks we have to take into consideration when we are taking our data. There are a few general precautions to be taken, that considering the recording intensity method. Crystal should be entirely in the X-ray beam. It should be entirely bathed with the X-ray beam. We should not have a crystal which is out of beam and we are taking data. We should not do that. And if we do this, then we will see that we are missing lots of information, as well as the data we collect may lead to us a incorrect crystal structure determination. Okay, so X-ray, and then X-ray beam should be as uniform as possible. These two general precautions we have to take very much into consideration when we are collecting intensity data from a single crystal diffractometer, either diffractometer or even film method. Or as I said earlier, that film method is now going to be more or less obsolete. It is only for classroom discussions or classroom demonstration. The significance of these requirements is obvious if one is to compare the relative intensity of two reflection. So we are comparing the relative intensity of two reflections. So if we want to compare this relative intensity, we have to take consideration of these two precautions very much. There are three major difficulties also. What are these? The scattering of radiation by processor other than Bragg reflection. We are looking for Bragg reflection, so we will have also other radiation in processes. We have to take care that we should not have any other processes in taking the data other than Bragg reflection. Spectral impurities. What do we mean by spectral impurities? That we do have in a spectra, do have copper K alpha 1, alpha 2, copper beta, say we are talking about copper radiation, copper K alpha 1, copper alpha 2, K beta, etc. So we have to find that as much as possible we remove other radiation which gives us streaks, which gives a false intensity data. An example is given here. If we take say a reflection 0, 10, 0, and we use copper K beta radiation, what we see that we get 13.9992 by V reciprocal lattice unit. If we take K alpha of the 090 reflection, and our radiation is K alpha, then we see that this is 13.876 by D and reciprocal lattice unit. You see, these two are very close, and therefore we might get some problem while analyzing our data. So to be sure that we do not have any beta radiation along with alpha radiation, or alpha 1, alpha 2, and K beta, all radiation are there. These we call spectral impurities. We have to be careful about spectral impurities. and need to define boundaries of reflection correctly. That when we want to take data by diffractometer, we have to correctly define our reflections regardless of variation, size, shapes, and intensity. So these are the points we have to remember very carefully when we take intensity data for a crystal to determine the three-dimensional structure. Okay, now we have to talk about unique data. What do we mean by unique data? That's what we have to discuss. That available data, any crystal is limited by the wavelength of radiation. We have shown it in our earlier lecture. I suppose it was the 13th lecture. That how much data we get with the copper radiation, or how much available data we get with molybdenum radiation, also to say other radiation. We can find out that this much data we can get once we define our limiting sphere. So as it varies with different radiation type, copper sphere and molybdenum spheres are not of the same size, different size, limiting sphere. Okay, we take into consideration these limiting spheres, and then we within the limit we can find out independent observation. What do I mean by independent observation? That a plane is independent. It is not dependent with other planes or other factors, I would say. So the independent observations, we will see that we are getting lots of theoretical data point if we use copper sphere or molybdenum sphere. Fortunately, we need not to observe all this data. We will only observe independent data, which are not dependent with certain symmetry elements or so. And we can also see that with the structure type, that means monoclinic, how much data we have to take, triclinic, how much data we have to take, and this sort of this we call unique data. So we will take this unique data in the next lecture, explain a little bit of unique data in the next lecture, and show how which part of the octet we can take and continue our determination of three-dimensional crystal structure. With this, I complete today here, and hopefully we'll start with unique data in the next lecture and complete data collection of a single crystal. Thank you very much for your kind attention.